for the usual T-Talk organizers who couldn't be here in person. So bear with me if there are any mistakes I make. As usual, you can help yourselves to some pastries and coffee back there. And yeah, today we have the honor to have one of our own, Dania, an assistant professor at Mila at the Department of Computer Science and Research Operations at UDM. She's a core academic member and a Canada CFAR chair. Prior to this, she was a postdoc researcher at the University of Columbia, and she received her doctorate at the University of California. Her interests are focusing on combining causality and machine learning research in service of AI systems that remain robust as the world evolves, adapt efficiently, and discover new knowledge alongside us. Couple of house rules. If you have any questions here in person, you can raise your hand and I'll give you the mic so that people online can hear you. And for people online, this time, since there are some issues, if you have any questions, just write them in the chat and I'll report them to Dania. And yeah, I hope we're gonna enjoy this talk. And Dania, the floor is yours.
Thank you, Sama, for I think that applause was for you. Thank you for stepping in admirably and courageously into this role as host. Thanks for everybody for being here. I know it's the time of year where it's really hard to keep consistently showing up to things, so I really appreciate this amazing attendance. Today, I'm going to hope to convince you of sort of just one high-level thing, which is that theory actually can continue to help us when we think about interpreting language models. So we've actually had many T-Talks already on this subject that's near and dear to my heart, causal representation learning or identifiable representation learning. Seb actually gave an excellent T-Talk on the same subject somewhat recently. This will build on that theory, that line of work, but now I'm going to show that actually I believe, and I hope to convince you, that this line of work actually has something to bring to the field of language model interpretability and the interpretability of other systems. Okay, so at this point, I'm sure I don't have to show these slides, but generative models don't always behave the way we want them to. Here's an example shared with me by a colleague where you ask it to draw an Indigenous doctor or an Indigenous nurse. It adopts these very, very harmful stereotypes, right? It also perpetuates various gender-based stereotypes. If you ask it to generate images of a nurse sitting in a white room, this was a few years ago, but these examples still hold true. You'll get a bunch of images of women presenting nurses. That's not in the prompt here whatsoever. We know that these systems are not robust to jailbreaking. We can form our prompts in particular ways. The language model will then give us answers to very harmful questions like generating new biotoxins or bioweapons, for example. All that to say that we're at a point now where we have to sort of be like biologists or like neuroscientists or cognitive scientists, right? We have this complex system that we want to understand. We want to pull back the layers. And so we need to adopt the scientific method. We need tools to interpret what concepts these large models know about what they encode and how they solve tasks. With that in mind, I'm now going to pivot to a very simple example to help set the stage what I mean when I say concepts, what I mean when I say interpret, etc. So let's consider a really simple task of training a transformer to do two-digit addition. Okay, so I have a very cartoonish illustration of this task. As input tokens, we may take in two-digit numbers, and we will ask for the output token to capture the output of the addition. Okay, and we're considering transformers where maybe what we're actually trying to understand and interpret would be the encodings in the residual stream of the transformer. So let's say we can train a transformer on a lot of two-digit numbers and their sums to do this task. Let's consider what an actual computation model for this task would be, right? This is maybe the computer program or the little mental model program that we would implement to solve this task. I would add up the digits in the 0th place. I would compute a carryover or a remainder term. Then I would add up the terms in the 2nd place and then add the carryover, right, to produce the output. So very simple example, but one question that we may have in a simple system like this is, does a transformer also know how to implement the carryover concept? Okay, so let's take a concrete example. I have here 16 and 25, and there's a carryover of 1. Okay, what would it mean for a transformer to know this concept or to implement a version of this concept? It would mean that in my computer program, if I were to change the carryover to 0, if I were to perturb, right, I would get the incorrect response of 31 now. Okay. I'd want to know, is there some way I can manipulate my activations such that I can mimic the same incorrect response in my transformer? Okay, that's what it means to try to find an alignment or an interpretation between some concept that we know about and the activations of a language model in this case. Now, in the previous picture, I was trying to see if the concept aligned with a single neuron, but for all intents and purposes, this isn't practical because concepts are typically distributed across the dimensions of activations or token embeddings, right? Or neurons in the MLP layers of a transformer. So the way that modern interpretability techniques work, right, in sort of a unsupervised way, we try to perform a change of basis. We take our language model activations, we try to find a different representation of those activations such that in this new basis or in this new representations, hopefully I will have these interpretable concepts. What does that mean now? Let's say I have a hypothesis that the last dimension of my learned representation encodes the carryover concept. Okay? If it does do so, then what I should be able to do, I should be able to encode my current activation. I should be able to perturb the concept in the latent space. And I will decode back to activation space. I'll get a new embedding now, right? And I should be able to paste this over to my transformer. And now I should be able to mimic that same incorrect output for this addition if the carryover was set to 0, right? I should get 31. So this is what we're hoping to do when we try to do unsupervised interpretability research. We're trying to see if transformers encode concepts in the same way that some kind of hypothetical model would use and encode those concepts, right? Which doesn't only entail a set of outcomes, it also entails a whole set of counterfactual outcomes when I perturb these concepts like I did with the carryover. Okay, so the canonical way, the popular way to do unsupervised concept discovery in language models and other kinds of language models like protein language models as well is to use sparse autoencoders. This is a pretty old idea. This was not invented by the recent interpretability community. This is an idea from signal processing. It's based on this field of work on sparse dictionary learning, where we have some dense signal, in this case, a vector of activations. And I want to decompose the signal into a sum of sparse signals. And typically a sparse sum as well. I want to use very few concepts in some latent concept space in order to represent my dense vector. Okay? Let me just pause here really quickly. Any questions? Okay. So the most recent instantiation of sparse autoencoders for interpretability of language models has been with this sparse autoencoder approach. So concretely, the way that it solves the dictionary learning problem is by minimizing this particular regularized objective. So what you're seeing here is you're trying to do autoencoding, right? You're trying to learn an encoding function to a learned latent space such that you can also learn a decoder that's hopefully its inverse that can reconstruct the activations exactly. But I also am going to add a penalty so that the learned representation is sparse. Okay. What this means is exactly what I said earlier. I want to represent my dense activation vectors in terms of a sparse number of latent concepts. Okay. Typically, and this is sort of illustrated in this image here, with a sparse autoencoder, the learned basis or the learned representation is over complete. There's more dimensions than we have in our activations. So there's this regularized objective. We see here that we are just performing a linear change of basis. So we're trying to learn concepts that are just linearly related to our activations. And if these concepts are actually disentangled, right? So if every single dimension of my learned space captures something that I can intervene on, like that carryover digit, right? Then each column of the decoder should give us some kind of direction in which we can steer, we can add this vector to all activations to mimic that concept change. Okay? That's the key idea behind this idea of steering, that I can extract these vectors such that if I add them to any example, to any activation, they should enact the same kind of concept change. So here, if I could find a carryover equals 0 vector, I would be able to manipulate a whole bunch of 2-digit additions. This is a big if, right? So we're going to really ask the question, do sparse autoencoders have this disentanglement property? And if not, what can we do? So there's been a lot of efforts to benchmark interpretability techniques, especially those that are unsupervised in the realm of language models. And I'm not going to go into this plot in a lot of depth, except to point out that these two axes, they're plotting certain evaluation metrics that, roughly speaking, look at how well different interpretability techniques can detect some kind of ground truth concept. Okay? In a benchmark where a bunch of concepts have been annotated and labeled, we're trying to see how well methods can recover and predict concepts, ideally ideally by using just a few dimensions of the learned vector, right? So if you've learned a concept vector, hopefully one concept vector suffices to predict some ground truth concept. The fact that sparse autoencoders have been evaluated to be in the bottom left corner suggests that they're actually not good at disentangling concepts. A single latent dimension doesn't seem to correspond to a single ground truth concept. Okay, so this is kind of the big punchline that I'm hoping to convince everybody of. If we're going to do unsupervised concept discovery, if we're going to use unsupervised learning to make scientific discoveries about language models, we need guarantees. We need techniques that can provably disentangle concepts, either for us to be able to understand what these systems are doing, or to be able to control and steer the behavior of models. Okay? So I really believe that unsupervised methods and guarantees have to go hand in hand. Okay, and to motivate this, I'm going to kind of take a big step back. I'll do a quick sort of intro to causal representation learning, which is a field of research that considers unsupervised learning methods, adds more constraints to them to make them identifiable, okay? Or that is, to ensure that they learn a set of solutions that have some desirable properties. I'll also call this the art of sort of discovering intervenable features, and we'll talk about what that means. But let's take a very different example. Let's say we want to do some clip style model where I have captions and I have images and I want to align the embeddings of these two things. So for simplicity, I'm not going to try to learn the embeddings of captions, okay? Suppose this is given to me. We'll call it G of Y. G of Y are embeddings that take captions as input and embed them into some space. The space is not particularly interpretable by itself. So the fact that the coordinates are where they are is not meaningful in this particular G of Y representation. I would like to learn a representation now of images that allows us to linearly decode back to the caption embeddings. Okay, that's how I'm setting up my objective here. It's a simple mean squared error objective that aligns two sets of embeddings. A nice representation might be this kind of f of x, okay? Or a whole bunch of such bases or representations where every single axis might be something I actually want to intervene on. Okay? So if I could actually automatically discover this kind of representation for every single image, it would be nice, because what I could do is I could perform these latent interventions, right? Interventions in latent space. And when I perturb a single dimension of the image's encoding, and let's say I decode back to image space, I'll change a single aspect of the image, right? In this case, I've changed the color only. I'm not changing where the ball is. So this is nice in that now I have kind of independent control on the kinds of concepts I would actually like to manipulate. Okay? Of course, I have to maybe search over all of the latent dimensions. I don't know which latent dimension corresponds to what kind of underlying concept, but I can perform these perturbations, and each perturbation results in some kind of meaningful change. But let's go back to our objective, right? And ask ourselves, is this nice representation something we're guaranteed to learn? And why is this nice? I've just picked a very nice f of x here, where you can convince yourself that the x-axis encodes left to right. It encodes position in the image. The balls only vary along the x-axis. And the y-axis changes the color. Okay? We go from blue to pink to gray. Okay, so this is a nice representation that would have had that nice intervenable property, the axis aligned property that I talked about. Are we guaranteed to learn it by just minimizing this reconstruction objective? That's the question. So let me just maybe ask, how many people think that we're guaranteed to learn f of x with this reconstruction objective? Nobody. Okay. So this f of x certainly is linearly related to this g of y. This is one of our many solutions. This is one in our set of global optima, right? However, so is this rotated solution. Okay. This has been rotated by 73 degrees. This is still linearly related to g of y. But you can see by the plot that I've done here in the background, the gradient of colors, now when I want to change color, I have to move in a very specific direction. If I want to take images and I want to perturb them to be pink balls instead of blue balls, I can't do any sort of axis aligned change now. Okay, this, why might this be bad, right? Inherently, if I just care about linear decoding, this doesn't seem bad. It's because what we typically want when we do unsupervised learning is to use the unsupervised representation for things like steering, for things like control, for things like understanding what the fundamental factors of variation in our data even are. And so now if I was to do an axis aligned change, many things about my image would change at the same time. Okay. So the axes of the learned basis don't align with the kinds of manipulations we want to make. From the perspective of the interpretability task that I set up earlier, now if I wanted to uncover a steering vector that allows me to just change images from blue to pink, I actually am back to my problem where now I actually need labeled data, right? I can't do anything in an unsupervised fashion. I would need some labeled data to be able to figure out in my latent space, what is the perturbation direction that moves me from blue to pink. So when I have this sort of indeterminacy, right, I'm stuck where unsupervised methods don't even make sense for interpretability. Yeah, Mehdi. Yeah.
So what you just said about the orthonormal, condition on the axis allow you to change the concepts one by one. But isn't just orthogonality between axes allowing you to do that as well?
What do you mean?
So you were saying that we need like something completely orthonormal, so that we would be able to change one concept by one concept. But if we rotate and our axes still remain orthogonal, can we still operate in this way or not?
So an actual rotation here. So let's take our kind of nice representation f of x. Even if I performed a proper rotation that maintained the orthonormality, I would still be hurt because the thing that I really want is for the bases to be aligned with the directions that I fundamentally want to move in. So yeah, that's a great question. But okay, good. So back to our problem. The issue is that the objective of just wanting to reconstruct is underspecified. We need to place more constraints if we want our basis to mean something. If we prefer one solution over another, I have to sort of name that solution in some way. There's a ton of literature in identifiable representation learning. This dates back to the 90s and maybe earlier, Seb would know, where people have been studying the identifiability of simple things like linear ICA, nonlinear ICA, and so forth. I'm going to highlight a sort of very simple result because it's really kind of easy to understand, and then we'll build on that for what it is we've been doing in our group for identifiable interpretability. Okay, so a very simple idea is that if you actually have perturbations, if you have paired samples where each image comes with a bunch of other paired images where we've perturbed a single latent dimension. So here we have a bunch of balls. Maybe in one paired image, I have moved one of the balls along just the x-axis, just done an x translation, right? In image space, the changes may look quite dense. It's not going to be a sparse change, but in latent space, this change is sparse. So what I can do now is I can have some kind of regularized contrastive objective that says, okay, I want to make sure that the embeddings of my paired samples are really similar to each other. And in fact, they differ by just a single concept difference or a single latent difference. Okay? And I can enforce that that difference vector is actually one sparse or p sparse. Okay? How we do this in practice, that's the machinery I'm going to ignore, but let's say we can actually enforce the L0 norm. What we get are results that you can actually now show that you're guaranteed to recover a learned representation that's equivalent to the ground truth one, up to a permutation matrix and a diagonal scaling matrix. Why is that significant? It means that we can actually recover the bases that we would like up to, maybe I can't exactly label my dimensions exactly, and I may have some linear rescaling of all my latent factors, but that's the only indeterminacy that's left. Okay. One thing to note is the way this works is via some form of weak supervision, right? In some sense, having one sparse changes, the changes kind of tell you what are the actual bases that I want, right? They give you some supervision signal about the directions that you want to move in that are meaningful. And that's how we are able to pin down that particular special representation. Let me pause here again for, yes.
If you have more than one thing changing at a time, but it's still more or less sparse. Okay, you're going there?
Great question. Yeah, I wasn't going to go there today, but if you have p sparse changes, you get identifiability up to blocks of p components. So now you won't be able to disentangle the factors that covary with each other. Is that not your question?
No, it is. I just have a.
Okay.
Although I guess. Is that true even if the things that are jointly being intervened on change? It's like I'm not always intervening on the same, the same exact block of things.
Good.
But,
You're saying like
I changed the the pairs or the triplets
Yes,
or whatever?
yes. Okay, then actually, then you get back to permutation
Okay.
results. Essentially, it's because you'll get kind of still evidence of, okay, maybe, you know, two things are changing at once, but sometimes dimensions 1 and 2 change, sometimes it's 2 and 3 change. So you'll still have some sort of non-overlap. Or overlap, yeah. Good. So this, if you're interested, I'm very happy to talk more about CRL. That's a whole talk we can give, and we've actually given tutorials on this at UAI and at Mila, so you can find this on YouTube if you want to watch 3 hours worth of this content. But now I want to bring it back to, you know, is this what's going wrong with SAEs potentially, right? Is there a reason to believe that the objective, even though it's regularized, is somehow underspecified and doesn't guarantee that you get disentangled concepts? That's what I'm going to explore. Again, this evidence is the picture to keep in mind. Intuitively, it seems like SAE should work because this is not a completely underspecified reconstruction objective. There's an extra constraint that says I want sparse representations. It feels like this should lead to something. So what could be going wrong? First things first, because we typically find an overcomplete basis with SAEs, some concepts are just not learnable in the sense that, you know, I'm throwing away information when I go from this overcomplete concept space to activation space. And so two different concepts or two different concept vectors can lead to the same activation. If that happens, I will never be able to invert from activations back to those original concepts, right? So another way of saying this is that the mapping from concepts to activations is not injective. There's just no possibility to even have a unique solution from inverting activations back to concepts, right? And that could be issue 1, right? There's also results in identifiability theory that you have to have some other sufficient conditions met in order to have identifiability with these constrained, sparsity constrained objectives. And fundamentally, the issue here is that if we lack some activations that capture just a single concept, there may still be, you know, solutions that entangle multiple concepts and that still minimize our particular regularized objective. Okay. This is coming from literature that says that, you know, to really get identifiability, you need at least some examples that show you what a single concept looks like in activation space. Okay, sometimes these are called anchor features. And so this may be sort of another issue with SAEs and what results in them, practically speaking, still entangling features. So what we're motivated by this as a starting point, and Shruti is here. If you have questions that are really, really hard, ask her. But this motivated us to consider if we can link the theory of CRL to being able to have some kind of interpretability method for language models, right? That's unsupervised, but that is identifiable. So this brings us to sparse shift autoencoders. And I'll repeat this many, many times, so you'll probably get the acronym by the end, SSAEs. And so before I kind of explain the method, let me explain the setting, because we work with paired data as well, but it's a very specific sort of new way of getting paired data, okay? So we work with what are called multi-concept shift datasets. Let me explain the generative process that we're assuming underlies the data that we have, right? So we assume that we have a bunch of paired samples, and the way that we get these pairs is you have some kind of concept vector. The concept vector generates some particular activation, and then you select some indices to perturb in the concept vector. So in this case, we've chosen index number 1 and index number 4 to perturb. Then I'm going to sample a change vector called delta. Okay? Delta C represents how I'm going to perturb the concepts in concept space. Okay? Then I'm going to get C tilde, which is a changed concept vector. Okay. Again, this is an assumed generative model. This is just a story that we're telling about the data that we have, right? Then we assume this is what gives rise to our paired examples that are text, x and x tilde. I can use an LLM to encode these two examples, right? Then I'll get z and z tilde correspondingly. The key thing is that now I can actually compute the difference between my embeddings in activation space. Notice the key sort of graphical illustration difference here as well. In concept space, the change was sparse. It only varied, the delta in concept space only varied along dimensions 1 and 4. In activation space, the change vector is dense. This is exactly what we mean when we say that the activations, right, they linearly mix up, they linearly entangle the underlying concepts. Like SAEs, I'm going to want to go back from my concept space, sorry, my activation space. I want to invert that back to concept space. That is going to be our goal. Okay, so I've sort of already motivated the method. Couple caveats, or a couple things I want to emphasize, rather, they're not caveats. These are strictly more general than single concept shift pairs. That's the first thing I want to emphasize, because in this data generating process, I am sampling with diversity different coordinates to change in my concept vector. Okay? This is not a single concept being perturbed all the time. It's not even a single concept, but where the concept varies across pairs. For example, you might be wondering, and it would be very good to wonder, how do you even get this data? There's many ways. In the paper, we've tried a couple of different things, including sometimes you can just pair random sentences together. Maybe you can take a corpus of Wikipedia sentences, maybe all the sentences on cities, for example, and you can match the period representation of randomly chosen sentences that would still meet the multi-concept shift dataset criteria, right? Or, we could debate that, but it arguably does. We could also now use LLMs to generate concept shifted examples. And we can now not worry about the fact that LLMs probably don't generate perfect counterfactuals, right? I can ask it to perturb the style while holding the content fixed, but invariably will perturb more than one thing. And now that doesn't matter because we use these multi-concept shift datasets. Okay, so again, keep this little picture in mind. We're just assuming that the data comes to be by this process where you've chosen some concepts to perturb, and you can represent the difference in embedding space. We formalize some conditions on how diverse the shifts have to be in order for sparsity regularization to actually provably lead to identifiability. So we sort of concretely address the amount of diversity needed. And what's kind of cool here is that previously we were worried about the over-completeness of our basis, right? We were worried about the fact that maybe there's way more true underlying concepts than there are dimensions of activations. But we actually, any concept that is not perturbed at all in my data set, right? There's going to be a set of concepts that vary in any given data set and a whole bunch of things that just never get changed. When we consider difference embeddings, right, those get canceled out. So now I only have to worry about trying to identify or to try to recover the small set of concepts that are perturbed in any given data set. So that's how we sort of get around this lack of injectivity that was plaguing SAEs. Okay. So again, the key detail to emphasize here is we do explicitly restrict ourselves to recovering the concepts, only those that actually vary in the data set, because everything else is going to get canceled out. So the architecture shouldn't surprise anybody. This is very similar to the sparse autoencoder architecture, where now what I'm going to try to do is invert my difference vectors into some latent space where the concept changes are supposed to be sparse. Okay. I've drawn an over-complete basis here, but we don't we've played around empirically with both, a very, very big basis. We've also played around with having exactly as many dimensions as we have in our activations. Okay, and we've also played with having much fewer dimensions than we have in our activations. So this is the algorithm. It looks very much like sparse autoencoders, the key difference being that the inductive bias that motivates a sparse autoencoder is to find a basis where concepts are used in a sparse way. For any given activation, I have to represent the concepts it uses, and I have to pick just a small subset of concepts. Our inductive bias is to assume that it's interventions that are sparse. It's not the activations that are sparse, it's the changes, the perturbations that are sparse. Okay. And so I'm just going to give the informal theorem. It's very similar to the result that we saw for weakly supervised CRL. We have a regularized objective, right, where one term is trying to encourage reconstruction, like all autoencoding techniques. There's another constraint that wants the learned concepts to be sparse. Okay, so again, I'm taking my activations, I'm inverting it to this concept space. I want those learned concept shifts to be sparse. And the informal theorem is that we can estimate these concept shifts, delta C, or delta C hat to be more precise, again, up to a permutation matrix and a diagonal scaling matrix. What this means also is that the decoding function is also identified. And it means that the columns of our decoding matrix, just like with sparse autoencoders, the columns are going to be parallel to the directions we would want to steer in. Okay? Each column is going to be parallel to some kind of concept steering vector. I say parallel to because of this scaling indeterminacy. Okay, so it's now time to look at a couple of results, and then I'll sort of end with my concluding thoughts. But maybe before I go into wander off into the results, any questions on the technical detail? Okay, so I'm not going to do the full suite of results that we have in our draft. I'm going to show a couple of the ones I think are quite exciting. So one thing that we did, right, besides use some standard metrics to evaluate, did we actually identify the columns of the decoding matrix, or did we actually identify concept shifts? We have some standard metrics to evaluate that, but we also looked to see how accurately can our learned steering vectors be used to actually just steer. So we have some held out pairs of data that actually do vary by a single concept. Okay, so we don't use these single concept data sets to train the sparse shift autoencoder. We have a multi-concept shift data set, train the autoencoder, evaluate on these single concept shifts. To any given Z, we apply our learned steering vector. Okay, these would be the columns of the decoding matrix that tell me how each concept perturbation should get mapped into activation space. And I'm going to compare the true steered embedding, Z tilde, that I have in my ground truth against the predictions made by using our learned steering vectors. Okay. The measure that we're going to use now to compare truth to prediction will be cosine similarity. So our algorithm, sparse shift autoencoders, is in purple. There's other baselines that, for example, take away the constraint or the regularization term. So we look at what happens when we just sort of have a underspecified objective. In blue is llama scope, which is sort of the canonical pre-trained sparse autoencoder for llama embeddings. And we have a few other supervised interpretability techniques as well. What we're finding is that sparse shift autoencoders on this specific task and the sort of small set of data sets that we have considered here are either very much outperforming SAEs, LlamaScope in this case, or very competitive with SAEs, right? Some of these tasks too are quite challenging. So one of the examples, as you see, is to try to find a steering vector to perturb the language that you're expressing a particular sentence in. And there's reason to believe that maybe language is just not something that is even linearly entangled in the last layer of a model, right? So some of these tasks are actually really quite challenging. It's not surprising that all the methods don't do that great. There's this sort of canonical evaluation, but we did a couple cool things as well. So we also looked at out of distribution steering. What I mean out of distribution here is we try to learn, for example, a steering vector to change pronouns, but we learn it on one data set and evaluate on a very different data set. So maybe the content of the sentences are really quite different. So we see how well we can do transfer. Again, finding that sparse autoencoders are actually quite brittle for this. Sparse shift autoencoders seem to be quite a bit more robust. We also had a really kind of cool corpus called bias and bios, where we have labels, we have these biographies of people that are labeled for both the gender of the person the biography is about and their occupation. We trained SSAEs on this corpus, and we evaluated all the different columns of the decoding matrix, and we found a steering vector that seems to really change the number of different gender pronouns. So if you apply the steering vectors to examples, you systematically get a lot more male pronouns versus female pronouns, for example. And what's kind of cool is that we compared SSAEs against GEMMAscope now, which is the canonical pre-trained SAE for GEMMA. And in order to get the same kinds of, well, actually, let me put it slightly differently. At any given steering strength, right, you see some differences also with GEMMAscope. If you search over all of the different steering vectors that GEMMAscope offers, you can see some perturbations that you're able to make to the number of gender pronouns. But for a given steering strength, you see a marked difference in the changes that SSAEs are able to implement. So again, we're finding some kind of qualitative evidence that the steering vectors that we're able to discover actually can change the behavior or the next token decoding of the model. Okay, so I'm almost done actually. So this should leave us with time for questions and a discussion. And I like to kind of take a step back and see the forest through the trees that we have been in for a while now. And so I think, by now, we're probably convinced that understanding the mechanisms and the concepts that language models and other large models know about, plays a central role in not only mitigating their unsafe behaviors, but being able to understand them the way that we understand any complex system or organism. If we have hypotheses about what kinds of concepts we expect to discover, there are certainly supervised interpretability approaches, right? The problem, or the thing that's really interesting though, is that in science, we don't often have a priori knowledge about what we're trying to look for. That's the whole point. We're trying to discover the meaningful dimensions of variation in our data. We're trying to understand things we don't understand yet, right? This isn't necessarily an unsupervised discovery challenge. And in order to do unsupervised learning, right, we need guarantees. This is fundamentally a scientific endeavor, but we need to be able to sort of falsify our hypotheses and make discoveries that we can then actually make some concrete downstream decisions using, right? And this requires some notion of reliability. And so this is why I think this is a really cool link between the long-standing field of causal representation learning and identifiability. And I think that theory does have a role to play in this research topic of interpretability, right? And so what I've told you about today is some techniques that we've been working on in my group, and there are other related papers that we've been working on recently that are about using the mathematical tools and methods that we've developed in CRL and bringing it over to the field of LM interpretability so that we can discover provably underlying sources of variation and concepts, even when we don't have any a priori hypotheses about what the LM might be doing. Okay, so that's basically the pitch that I wanted to end on, that we should think of interpretability as a science. And let me sort of stop there. Thank you for listening, and I'm very happy to have a discussion now.
Thank you. So a lot of concepts in reality, I think, might be like compositionally related. In other words, maybe there's a million concepts that we could think of, but they're not all just like independent indices. It's like some concepts are, in a way, nonlinear functions, perhaps, of others.
Yep.
Do you think that this would be able to handle that? Like, I mean, if you trained on some set of, let's say, basis concepts,
yeah,
and then you fed, I don't know, two texts that differed according to, new concepts, do you think that they would look like compositions of these discrete concepts in your learned sparse space?
So that's an excellent question. There's probably something misleading about me saying basis sometimes, because in this field of causal representation learning, actually, what you can identify would be a set of concepts that could actually be related by a causal graph over them, or maybe some complex function over them. So this may not actually be a proper basis, right? They're not going to be independent vectors. What might happen is that you discover a set of concepts that are actually going to be related by some, noisy or maybe even deterministic functions. So you could discover these kinds of compositional concepts. What would also be interesting is to apply these techniques across different layers of a language model to see if maybe composition is happening sort of across layers as well.
Thank you for the talk. You have mentioned that to analyze the representations of your large language model, you study the last layer and the last token. Have you tried playing with other layers, and have you observed some phenomena such as losing information if you look at the last token versus others?
Brilliant question. So we have looked at different layers. Here's something that's kind of interesting. So sparse autoencoders as well, they apply a ReLU, but really they're trying to learn a linear unmixing function. Right? You're trying to go from activations to some sort of linearly related set of concepts. There's no guarantee, technically speaking, at earlier layers in a network that concepts are going to be only linearly entangled or mixed. At the last layer, because the pressure on the language model at the last layer, last token, is to do linear decoding of the next token, arguably you can make a case that concepts are actually going to be only linearly entangled. So that's our kind of theoretical motivation for studying the last layer, last token. Nevertheless, we've sort of done sensitivity analyses to study earlier layers. I don't remember exactly what our findings are on this. You can ask Shruti. I think your question about other token embeddings is a very, very good one. And I actually share this sort of curiosity to want to investigate because, again, because the pressure to linearly decode is really on the last token, it's possible that, earlier tokens might carry a bit more information, and maybe there's some kind of compression happening for the specifically the last token. It's a hypothesis, but one that we should test systematically. Yeah.
I have a question about it.
Yeah.
So Michael Smith says, you mentioned downstream tasks. Can you give an example of how information about what is learned by the network can be used in a practical deployment?
So typically, what people want to do if you learn a steering vector is to try to apply it in novel contexts to see if you can change the decoding behavior of a language model. So some of the canonical examples have been actually in AI safety, where you try to learn a steering vector for refusal, and then you try to apply it to prevent the model from being as vulnerable to jailbreaks. That's kind of the sort of practical use case of steering. Can these sparse features be used for downstream prediction tasks? Yes, but it's not clear what benefit they would carry above and beyond just using the LM activations in the first place. So I think the reason to care about identifiability and having these kind of nice axis-aligned features, right, or features where the axes mean something interesting, I think it has to fundamentally be motivated by some kind of intervention-based task downstream, or some kind of just understanding-based goal. I think just pure prediction performance is never going to sort of prefer identifiable representations over non-identifiable ones. Yes, clear. I'll just repeat the question. Yeah, sorry, say your question again. Into what? Interpretability, yeah. So what we've leveraged are results and flavors of results from this field of causal representation learning. The key thing is to make this link, we're observing that interpretability fundamentally poses a unsupervised learning challenge, and that the kinds of interventions that we want to make here necessitate some notion of identifiability. So that's the starting point. And for example, the multi-concept shift data set that we use and the regularized objective, these kinds of paired sample data generating processes and the proof techniques that we use to show that this particular sparsity constraint leads to identifiability, these have all been borrowed from the field of CRL.
If people online have any questions, you can write them in the chat. For the person having questions, we still have time, 5 minutes.
Okay, this question is a bit, maybe I was too much in my head, but basically you mentioned the field of jailbreak in LLMs, right?
Yeah.
So what the little I know from this field, for example, is that you have certain attacks or certain suffixes that you add in the end of your sentence that do not make any sense at all. So these are considered perturbations as well.
Yeah.
So would you think, using your methodology, you can come up with attacks that are somehow interpretable, like, perturbing now the input in a way that we can understand, and that still works to jailbreak an LLM?
So it's really interesting, because following the thread of some of the examples I gave here, this would almost be more like finding attacks in latent space. Like using a sparse autoencoder, a sparse shift autoencoder, what you could do is find some other latent space, or what we're fundamentally doing is finding a latent space that differentiates, let's say, successful jailbreaks versus non-successful jailbreaks. So maybe one of the latent concepts that we learn will have to do with successful jailbreaks, some of those jailbreaking mechanisms, for example. But I think that's a really interesting question of, okay, what is now, if you learn this kind of concept, can we further regularize and say that this has to decode to some set of tokens that are human interpretable? I think that's kind of the next step, perhaps, to getting the kind of thing that you're saying, where the change in latent space also corresponds to tokens that are meaningful and not sort of garbled set of tokens that are incoherent.
I think I have a question.
Yeah.
For you, if I may. In scientific discovery, you can you can observe a video of something, a phenomenon, and then you want to extract what a lot of people call intrinsic dimension, to know exactly what are the components that change, which is very related to what you presented. I don't fully grasp like the intrinsic dimensionality, because I've seen a lot of definitions for it from paper to another. And in this case, would you just set, for example, the concept vector to a a huge dimension, and then just hope that that you recover exactly the concepts? And if you don't know the intrinsic dimension, then how would you go about estimating it?
I think it's a wonderful question, and I see Shruti nodding in the back. I think she's got a lot of sort of thoughts on this. That's work in progress, and we're exploring some of this empirically mostly. I'm sure there is theory on this, but you touched upon something that's really quite interesting and good to note, which is that a lot of theory, especially identifiability theory, assumes that you know the ground truth number of factors. So, I mean, the theory works by saying, okay, there's K underlying factors. I want to invert from my observations back into a latent space that has some very simple bijection with those original factors, right? But the theory works by assuming that the learned latent space is the same dimension as the ground truth. So that's theory, but you're right that in practice, for many reasons, like over-parameterization, over-completeness seems to really help, right, with optimization and so forth. So in practice, what may work better is to have an over-complete basis. You may still get really nice disentanglement. Maybe now it's not a one-to-one simple mapping. Maybe now you have a few, you have sort of a subspace, a few learned features that correspond to one underlying feature. You still have some form of disentanglement, but it's not as nice as the one-to-one mapping I explained. But I think this is kind of where the theory has to go next.
Thank you. We have one last question online.
I think one last question in person too.
Okay, one online, and then we go to you. So by Maxime, when creating the multi-concept shift dataset by an LLM, would it be a problem if the misaligned LLM adds systematic bias in the form of a non-requested concept present in all pairs?
So there's some concept that always changes. Maybe that's how I'm going to interpret this. That there's something that like there's sort of no variability and it just sort of fundamentally always changes. If this happens, no, actually, yeah, this is a problem. So the theory says that you will always entangle that one concept that's always changing. So, and with all of these things, there's no free lunch. Like we have a sufficient diversity condition that we outline in the paper. If that's not met, you can't expect to get full disentanglement. But our hope there would be that you still have some limited form of disentanglement. Maybe you're only entangling all of the concepts with that one sort of pernicious concept that always co-varies with everything. But hopefully you can still get some disentanglement among the other concepts.
Okay, so this might be a more high-level question. In your talk, you mentioned that the techniques are at least partially inspired by the field of neuroscience. Like the overcomplete basis set thingy. I think this was like neuroscience research.
I said signal processing, but it could be that it's.
You had this one.
Yeah.
You had this Olsen and Field citation for the visual cortex. I think. Okay, so then maybe the question doesn't make really.
No, but ask it anyway.
Okay, so the question would be like, do you think the techniques might be of use in? So the techniques you presented would be useful in neuroscience to, push this front a little more.
That's a great question. So let me answer in a kind of indirect, long-winded way. So I know that sparse autoencoders and such techniques, and I hope actually SSAEs as well, could be applied to other kinds of foundation models, so other modalities like protein language models, for example. There, I think it's even more important to have good unsupervised methods because we really don't have as many hypotheses about what concepts we expect to find. In that vein, I am sure it would be really cool to apply these techniques to understand, for example, what neural foundation models might be doing. I think that would be a very, very cool application of this kind of work. And I guess Eric would like to probably answer the question for me.
Can't you just do it with neural recordings as well? 'Cause why do you need
Yeah.
to access the whole model?
Yeah, that's a very good question. Yeah, you could also apply these techniques directly to observations like neural recordings. That actually is basically done. Like this is the field of nonlinear ICA. I was talking about that as being sort of the basis of identifiability research. They were really inspired by these kinds of questions. That is the question of separating a set of signals into canonical sources that capture independent kinds of concepts or independent sources, right? So some of those techniques have already been applied to neural recordings directly.
You'd be able to use your exact same method for generating the data. Like you could actually use those same LLM sentences, present them to a subject, and then record the differences between activity elicited by sentences that varied across some factors.
Okay, yeah.
And learn those same
That's right.
sparse concepts from neural
Yeah,
data.
that's right. Like using a human to encode
Yeah, the human as a neural network.
text. Yeah, the human is a neural network. Wow, what a world we live in when we're talking about humans as neural networks. Yeah, I think that's exact. I think you can absolutely do these things. Yeah. I think that's it. So, well, thank you everybody for attending.